Hello everyone. I'll be discussing three questions about work and energy in this video. Yeah, so let's start. So look at the first question here. A small bead of mass 550 grams is released from point A and slides on the frictionless track in figure below. So let's go determine all the energy involved located at point A. So what we have here at point A is just gravitational potential energy. So I'm going to put it here UA like that. So at point B, we have two types of energy. We have kinetic energy because it's rolling down like this, right? When it rolls down like this. So we have kinetic energy at point B, but since we still have the 3.2 meters over here, it means that we have gravitational potential energy. I'm going to put it here as UB. What about point C? So we have a height here. We have 2 meters. And of course, it's going to rolling down with the velocity. So we have here kinetic energy at point C and also the gravitational potential energy, which is UC. Now let's start with the first question, question A. It says that we're looking for the beat's speed at point B. So we're looking for VB over here. All right, let's do the listing first. So we have the mass given here, which is 50 grams, and we're going to list it in SI unit. So that becomes 0.05 kilograms. What else do we have? Oh, we have all the values. We have HA, we have HB, and we have HC right there. Since it's looking for velocity at point B, we are definitely going to use this K because we know in kinetic energy, the equation has half mv squared, and that's what we're looking for this one. So we're going to use principle of conservation of energy, summation of energy initial equals to summation of energy final. The U at point A is equals to U at point B plus kinetic energy at point B. U is mgh, and because it is specifically for height A, we're going to put it here like that. But the UB, and for the UB, we have mgh, height of point B, plus half mvb squared. It's very specific for the velocity at point B like that. You know what? I see that we can cancel out the mass. Yes, like that. Substitute the value of gravitational acceleration, and then the height at point A is 5 meters, and the gravitational acceleration again is 9.81. Height at point B is 3.2 plus half. The VB is the one that we're looking for. All right. So when you do the calculation, you should get the answer 5.94 meter per second. There you go. And now we want to answer question B. Determine the net work done by the force of gravity in moving the bead from point A to point C. Now this question is asking for the net work done by the gravity. So we're just looking at the y component of all the forces. Here what we have, the displacement along y-axis, it starts from point A and end up at point C. So we can put it here like this. I'm going to put it here as like this, equals to 5 minus 2 meters. So we got 3 meters. Okay. And then from there, we're going to do the work done. Work done by the gravity is equal to force times displacement cos theta. And because it is done by the gravity, we are actually looking for weight. Okay, so it is mg times displacement, and it is cos 0 degree. And your final answer is 1.47 joule. That's it for question number 1. Now let's go to question number. Alright, let's read this question. A 2,500 kilograms car moves down a level highway driven by a 1,000 Newton forward force exerted on the drive wheels and a 750 Newton resistive force by the road. Find the speed of the car after it has moved 20 meters, assuming that it starts from rest. Oh, so many information we can get from here. Alright, let's do the listing. We have mass, that is 2,500 kilograms. And then we have push force, that is 1,000 Newton. What else do we have? We have friction force, and that is 750 Newton. And then the speed of the car moved 20 meters. So this is the displacement, 20 meters. Okay, it starts from rest. This is another information that we can put there. It is 0 meter per second. There you go. So these are all the information that we have. Now we are looking for find the speed. So we are looking for the final speed. What is that? Okay, let's get the work done first. Okay, the work done, W equals to force times displacement cos theta. And because the force here is along the displacement, we have force to the right, and then we have friction to the left, and we know that the car is moving on the same direction as the force. So the theta is 0 degree. Alright, so let's get the F net first. In order for us to get the F net, it is force here, over here, minus the friction over there. So F minus friction times displacement cos 0 degree. The force is 1,000. The friction is 750. The displacement is 20 meters. The cos theta, cos 0 degree is 1, and your answer is 5,000 joule. There you go. And now let's find our final velocity by using work energy theorem. Work equals to K final minus K initial. There you go. So we have 5,000 equals to half mv squared minus, you know what? I'm going to put it here 0. Do you know why? Because our initial velocity here is 0. So straight away, we're going to put it here 0. The velocity is 2 meters per second. That's it. That's the answer. Alright, let's read the final question. A boy on skateboard starts from rest on a 12-meter incline, ramp 20 degrees with the horizontal. At the end of the ramp, he continues moving on the horizontal floor. If the coefficient of friction on both surfaces is 0.15, how far does he move on the horizontal floor before coming to rest? Alright, this is a lot to take in. But you know what? It is much easier if we just do the sketching first. So we have the ramp, 20 degree. This is 12 meters. The surface of the ramp has a friction which is the same as the floor, the horizontal floor over here. And the coefficient of the friction is 0.15, the same with the horizontal floor. Alright, from here I think we definitely have to do the free body diagram. What I have here, the friction definitely going up, which is resisting the motion. We have a normal force right here. Then definitely the weight straight down, and our angle, which is in line with the normal force, and the theta over here is 20 degree. The acceleration definitely going the other side of the friction over here. Now let's do the equation. So what I can see here, the summation of force at component X is definitely equals to MA. The equation for the friction, F equals mu N. Oh, we have to find N. So we can do that by getting another equation from the Y component, and judging from here we can see that we have normal and we have WY. So normal equals, I'm going to do straight away, normal is equals to mg cos 20 degree. Can I do that? Okay, so let's see the boy's mess. We don't have, oh my God, it's okay. You know what? I think we got a pattern over here. We can see the pattern. All of these have m's. So yeah, definitely we can do something with it. We can cancel out the m, I think. 20 degree minus mu. This one is mg cos 20 degree equals to MA. Can you see that? That we can cancel them all the M's? That leaves us with something, and that will give us the A. You can find the acceleration, kan? Alright, let's do this. 1.972 meter per second per second. There you go. Alright, why would I want to find the acceleration over here? Why would I really care about it? Well, what I think is this is the initial velocity. Definitely it is 0 meter per second, right? As the boy going down the ramp, the acceleration is so high. So it is 1 point. We just found it just now, and that is this value. I want to find the final velocity over here. What is that? And because you know what, from there I can use kinematic, because my plan is to use v squared equals to u squared plus 2as, and then this u over here is the final velocity going down the ramp. You know what I mean? Because the acceleration over here, I'm going to put this as a1, is not the same, definitely not the same as the acceleration as the boy going along this horizontal floor. Yes, because realistically we can see that when we go down the ramp it is much faster, right, than when we go on a flat surface like this. What I got just now is the acceleration. For me to get the v, where this v is going to be the u for the second motion, which is on the straight horizontal floor, so that I can get the v over here equals to 0 meter per second. You know what I mean? So the u, this is a u1, this is the v1. Okay, and the v1 now becomes the initial velocity for the second motion, which is along the horizontal floor before it stops at v2 equals to 0 meter per second, right there. Yeah, so that's what we want to get. That's our plan. So now that we have the acceleration, definitely I can get the v1, so that it becomes u2. Okay, I know it's quite confusing. You can pause the video, you can repeat my explanation just now. Yeah, so let's proceed with our plan, which is to find the v1. So let's find the v1. I'm going to use the kinematic here, equals to u1 squared plus 2as. But do I have the s? Yes, I do. I do, and that is 12 meters over here. Yeah? Okay, let's do this. So the v now is 6.88 meter per second, and this one now becomes u2. Okay, sorry, this is v1. This is, I forgot to square root everything. I'm gonna put it like that. You know what, just put it like this. There you go. All right, now that we got the V1, it now becomes the U2. If we go back to our sketching, the free body diagram along this part is now very different from along the ramp. This is the free body diagram for the ramp, and now we have to draw another free body diagram that is for along the horizontal floor. So let's do that. What we have is the body and the friction definitely moving on the opposite side of the motion. We have weight down here and we have normal force going up. Do we have external force? No, we don't. And in fact, the acceleration is going backwards because our final velocity equals to 0. Means that this object is decelerating. Yeah? And we got our answer 1.4715 meter per second per second. And when you see this, it's very logic. We can see that the acceleration for the second motion, which is along the horizontal floor, is much slower, is much lower than the acceleration that we have calculated for the inclined plane. This is 1.972, which is almost 2 meter per second. While for this one, for along the horizontal floor, it is only 1.5. Yeah, 1.5. So it's much slower. It's very logic. It's very realistic. And now let's go to the final step using kinematic of linear motion to get our displacement. This time it is V2 in U2 and A2 there. When you calculate, you're gonna get 16.1 meters. There you go. So that's your final answer, and I hope you can, if you don't understand, you can repeat, you can pause, you can slow down the video so that we can process the whole workflow. Right? Thank you, everyone.